Let's solve yet another problem involving an ideal gas in a closed system. 20 cubic feet of air at 600 degrees R and 100 psi undergoes a polytropic expansion to a final pressure of 51.4 psia. The process follows PV to the 1.2 power equals constant. The work is 194.34 BTUs. Assuming the ideal gas behavior for the air and neglecting kinetic and potential energy effects, determine A, the mass of air in pounds mass and the final temperature in degrees R, and B, the heat transfer in BTUs. Let's lay out our storyboard for this problem. We have a piston cylinder assembly filled with air, and the air in the piston cylinder is our system, as designated by the boundary line around the air molecules. For this, let's summarize our given data. We know that at state 1, the pressure is 100 psi, and that's an absolute pressure. The temperature at state 1 is 600 degrees R, and the volume at state 1 is 20 cubic feet. At state 2, we know the pressure is 51.4 psi, and that's an absolute pressure. We also know that the molecular weight of air is 28.97, and the process 1,2 that takes place here is an expansion process. It follows the equation PV to the 1.2 power is constant, and the work performed during this process is 194.34 BTUs. Let's draw this process on a PV diagram. So we're out here at the gaseous phase. There's no vapor dome anywhere near this PV diagram. So state 1 is at 100 psi and has a volume of 20 cubic feet. The temperature, which is constant temperature lines, go down to the right on a PV diagram. It's 600 degree R. Now this process, PV to the 1.2 power is constant. It always follows a concave line. And that's going to arrive at state 2, where the pressure is 51.4 psi. The volume has an unknown V2, and the temperature has an unknown T2 value. Our model for solving this problem is that we're dealing with a closed system where we're going to ignore kinetic and potential energy changes. The polytropic process has a value of n equal to 1.2, and the air is assumed to be an ideal gas. And we are looking for the mass, the final temperature, and the heat transfer that takes place during this process. Well, first, let's solve for the mass in the system by using the ideal gas law and apply it at state 1, where we know everything we need. By rearranging the gas law, I get that the mass is P1V1 over RT1. Well, I know P1 is 100 pounds force per square inch. I'll convert that to square feet. I know the initial volume is 20 cubic feet, and I know the gas constant for air is 1545 divided by the molecular weight of 28.97, that having units of foot-pounds force per pound mass R, and the temperature is 600 degrees R. So I calculate that the mass of air in this cylinder is 9 pounds mass. Now let's find the final volume of the process. We'll do that using the polytropic equation. We know that P1V1 to the 1.2 power is equal to P2V2 to the 1.2 power. Let's solve for our unknown. Let's isolate the V2 expression. So we have V2 to the 1.2 power is P1 over P2 times V1 to the 1.2 power. I will now raise both sides of the equation to the 1 over 1.2 power, and that will leave me with V2 is P1 over P2 raised to the 1 over 1.2 power times the original volume. So I end up with V2 is 100 psi divided by 51.4 psi. That expression raised to the 1 over 1.2 power times the original volume of 20 cubic feet. And I get a final volume of 34.83 cubic feet. Now let's solve for T2. And again, we'll use the ideal gas law that PV is MRT. So rearranging for my unknown, T2 is P2V2 over mR. P2 is 51.4 pounds force per square inch. I'm going to convert that to square feet. V2 is 34.83 cubic feet, which we just calculated. The mass is 9 pounds mass, and the gas constant is 1545 over 28.97 foot-pounds force per pound mass R. And that gives me a temperature of 537 degrees R. Now, we need to find the heat transfer, and we'll do that with an energy balance. So an energy balance for a closed system, when delta KE and delta PE are ignored, reduces to delta U is Q minus W. I'll rearrange this for the unknown Q, and I get Q is equal to delta U plus W. Well, you may recall that work was given in the process, so I only need to find delta U, and I will rewrite delta U as the mass, which I know, times the specific internal energy at state 2 minus the internal specific energy at state 1. So I need to find values for U2 and U1. So I'm going to find the values of specific internal energy at state 1 and state 2 in a table. And the table I'm going to use is called the ideal gas properties of air. And we'll see that because air is an ideal gas at these states in the table, that my properties, for instance, enthalpy and internal energy, are functions only of the gas's temperature. So I can find values for U in this second column. And I'll see that at state 1, where my temperature is 600 degrees, U is just a function of this row of 600 degrees. And I get a value of U as 102.34 BTUs per pound mass. Likewise, at state 2, U is just a function at 537 degrees, so it's right here. It's 91.53 BTUs per pound mass. Now I can solve the problem for the heat transfer. We said that Q was just the mass times the change in specific internal energy, the values I just got out of the table, plus the work term, which was given in the problem statement as 194.34 BTUs. And so I can calculate that the heat transfer is 97.05 BTUs.